life comes down because I have anything. Okay, if pivot see the maximum stress, therefore the fatigue, because when it is bended, you have a maximum top and bottom. It will go through neutral axis 0, it varies. But when specimen subject to axial, any cross section, it will be seeing the intensity of stress everywhere same. That's why it will have a life is less. So if it's a pure bending, of course it is 1 to 1, there is no load creation factor 1. Pure axial is 0.7, pure torsion is 0.1. Combined loading, provided these factors are applied if you do testing in individual conditions. Sometimes you will have a both combination of torsion, bending or axial, all thing. In that case, you are taking consider, but one has to go very deep into that. That Sigley book is there. Have you people referred Sigley?
Yes, we are referring Sigley.
Yes or no? So that particular fatigue thing is given nicely given this thing. And this is very generic one. Sometimes what happen, you are taking SN curve from Axial, MMPDS or handbook which is generated in Excel, but your application structure which is you are trying to predict the life, it will be subjected to bending all the time. That endurance limit go up actually. That's a beneficial, but we don't consider. You take as the same thing like that. But if it is axial to torsion, it will come down. This is called measured loading and target loading. So measured loading which what is the one which has been tested, but in actual component level the type of loading it sees experienced during the usage. So this is the thing, it will have a reduction factor, except torsion to axial, it will again 1 point it will increase, because torsion is again is subjected to the 95% only, right, outer ring, but axial will subjected to, so you will have a beneficial effect. Torsion to bending 1.72. This varies, don't take it as bench, but whenever you are to taking up some project to execute thing, you have to refer the appropriate standard handbook or this manual to report that. Now surface condition. So you know again test has been done under mirrors policy. You see the top one. It is again given for the material, ferrous material. In x-axis bottom is an ultimate strength in SI unit, Gibbs, and top of course ultimate strength and building hardness, they are interrelated. You can refer to that, but mirror polish there is no size factor, surface factor required. But if you depending on the whether it is a fine ground or machined and hot rolled or forged, you can see how the factor keeps on decrease depending on the ultimate strength of the material. Of course, for aluminum you have to find that this is, but it's for ferrous material. So in that case, obviously smoother the surface, the longer it takes to initiate the crack. And there is another way of surface condition. If you people have happen to observe on manufacturing drawing or component drawing, in the bottom right corner there will be so many parameters mentioned. One of them will be surface condition, triangular, double triangular, and all of those are familiar with the D and T. So that is, so the size will be there in the terms. So in that case, luckily either one can use a graphical form, but luckily it is available in numerical formula, where depending A and S, please don't confuse with A and B is what we studied in Baskin's equation, that is different. But you once you know the ultimate strength of the component, and A and B depending on the type of surface finish, whether ground, machine or cold run or hot roll, then you can substitute that value, you can get the surface condition factor. Now temperature, obviously there is nothing much effect occurs unless you go into melting temperature. That is called 50% of melting temperature, the temperature at which your metal melts into the liquid. Okay. Then high temperature, of course, that is affecting only in the ferrous material, and for non-ferrous up to 450 degree or I think there is no change until factor 1. But in ferrous material, depending on the what range of temperature is being operated, you need to calculate the factor. Then reliability factor, because you have a lot of scatter in the test results, and it is a very statistical in nature, and it is reliability is defined as a 1 minus of probability of failure. Since the SN curve is 50%, 50% of probability, so in that case you take a reliability as a 1. Okay, but if you want more reliability, to have a more confidence level, repeated 9.9, you have to bring down your endurance by 62%. That means your operating stress will have to come down. If it is above that, then I will show the example. Now miscellaneous factor, this is very qualitative nature, but OEMs and all, they do have developed their own database for known factors. So it can be residual stress. So when there is a thing is bent, obviously the top surface will be seeing tension and bottom will be compression. That's as usual, there's not an issue. But once you leave the load, then your bottom will become residual stress and top will be compression. Then directional characteristics from the cold working. So when you do reduce the thickness, some grain boundary, they fall into the certain direction. It's called a rolling direction or longitudinal direction. Case hardening, generally it's heating is done on the top surface of the ferrous metal for some purposes. That also affect your factor. Then corrosion, exposure in the environment. Then electroplating, there is a requirement, some component towards the machine is there, it has to be provided with some shining color. So you have to do electroplating. In the process, it affects your fatigue life also. Then cycle frequency, it depends on, of course, there's nothing much cycle frequency as long as in high cycle fatigue, but it does affect is a corrosion, if it is a corrosion fatigue. Okay, depending on the time exposure is been shown and all, but it does affect the frequency, and also then the radiation effect, and then so those things. So now to sum it up, what are the factors? This is the different factors we already discussed, and the reference source is available. This anyway, I'll be sharing the PDP, but not today, not tomorrow. Then later on, Sai can share with you people.
Sir, one question.
This is all taken from.
So residual stresses are beneficial to fatigue. Is that applicable on all cases?
Tensile residual is determined.
Compressive only
beneficial.
Okay.
I will explain you one topic when it comes to residual stress. Then this is a load modification factor that we saw that. Temperature is of course the thing, and reliability. Then everything miscellaneous is a corrosion, surface treatment. Like if you have a chemical milling has to done. People are aware of this. What is a skin pocket? I think you say some people are new, means they are from other industry or in aircraft things.
Aircraft only, sir, but experience-wise, they less.
No, okay. Skin pocket is the. Anybody can tell what is a skin pocket? Experienced people. In a
any openings, right? Any penetrations?
No, not opening. Still, no. Skin pocket is
chem milling.
Area between two.
Chem milling, yeah.
Chemical milling. They do to reduce the thickness, because the sheet comes in the standard thickness. It may be 1.6 or 2 mm like that. But in the analysis, it shows the skin between the frames, two frames and two stringer. Usually, the standard benchmark is around 500. It will vary. I'm talking about single L. In the center fuselage, it will be around 500, and stringer to stringer, it will be 180 mm. But if you go towards the rear, obviously, frame distance will differ, but the benchmark. So that's called skin pocket. If analysis shows that 1.2 mm is enough, but you cannot, but you are having a 2 mm or 3 mm is the sheet, but in the skin pocket it needs only 1.2. You have to reduce. 2 means 0.8 mm to reduce. Then you have to do the chemical milling. If you do chemical milling, again it will affect the life. Okay, that has to be evaluated. I have a nice qualitative picture down the line.